All right, there we go. Awesome. All right, have fun, everybody. Hello, everyone. It's 1:30, so we'll be starting. We have a lot to cover today. Welcome to the Advances and Applications of Artificial Intelligence in Meteorology. My name is Anne Dacres. I'm from ECCC, and I'd like to introduce Miguel Tremblay, my boss, also from ECCC, and we'll be the co-conveners for today's session. It's actually our third year here with this same session, so we're really excited to see how it's evolving. And there are other sessions to come, if I am not mistaken. So we're covering all kinds of things. We're going to see what's happening at ECC in terms of weather forecasting and integrating AI. We'll be looking at how ECC is training their workforce to better understand and see the potential of AI in their everyday work. And we also have some special guests with us today. We have a local, Raymond, who will be presenting PARADIS, a physics-inspired neural network with learned semi-Lagrangian advection. And Parvin Garfarian, who will be introducing her work on enhanced short-term forecasting of meteorological variables using stepwise regression. So it's a case study of Kzno Lake Basin. So without further ado, I'd like to introduce my colleague, Christopher Subik, who will be joining us virtually. So Christopher, can you hear us?
Good afternoon, everyone.
Perfect.
And we can hear you as well. So,
Perfect.
Christopher, the floor is yours.
All right, thank you very much. Thank you, everyone. I'm pleased to be here, virtually, if not physically. And I'm here to talk about the recent developments of AI weather forecasting at ECCC, specifically with focus on atmospheric forecasting. As everyone in the room knows, this decade has been transformational for the field of artificial intelligence and machine learning in essentially every area of life. This is most common in private sector, where you can hardly open a newspaper without tripping over ChatGPT this and Grok that. But it also has hit image generation and classification, language processing in general, text to speech. But a main question until a few years ago was, would this beat out traditional scientific computing for weather forecasting? The AI field has, well, AI in weather forecasting has a long academic history, but it really came on the scene about 2 years ago now with the nearly simultaneous release of Pangu Weather, ForecastNet, and GraphCast. All of these were medium to large scale AI models that claim to essentially beat the then leading global forecast system, ECMWF's IFS, at an operationally relevant resolution of quarter degree in operational like configurations when initialized from a viable analysis. Now, weather forecasting is a big business. Not only are there private sector companies in this, but um, governments worldwide are involved, and there are relatively large budgets for this and even larger economic and safety impacts for the public. One study relating to NOAA suggested that every dollar put into weather forecasting there generated something like $10 of public value. So AI forecasting here put everyone on notice. And is there a better way to forecast the weather? This talk is a mix of the past, present, and future. The past is covered under the ECCC's AI roadmap and its adoption and implementation and how that's doing. The present section of this talk are the current and near future projects that have built, deployed, and are ongoing to improve data-driven weather forecasting systems. And I'll conclude with a somewhat speculative look about where the future of this field is going, both at ECCC and elsewhere. This is a high-level overview of what amounts to a very technical subject. I'm going to take the speaker's privilege to talk a little bit about the work I myself have done. Feel free to ignore that part. And this is, again, the perspective coming from the Meteorological Research Division of ECCC, specifically the atmospheric forecasting section. So I'm in the weeds of this subject, and I'm definitely the most conversant about it. But in addition to what I speak about here, there's other work going on ocean forecasting, air quality, regional forecasting, high impact events, and we could be here for days to talking about everything. Okay, so in terms of what's going on at ECCC, like essentially every other weather center, we were pretty well blindsided by just how quickly the machine learning based weather forecasting advanced circa 2023. Uh, we, like every other center at the time, didn't have a deep bench of in house AI expertise, but we've been slowly augmenting this through internal training and hiring. Um, and like every other weather center, we have a huge uncertainty on how we can integrate these AI approaches alongside traditional systems and while meeting government mandates. We can't put our head in the sand and ignore the extremely attractive performance and accuracy claims of these systems. But on the other hand, we also need these systems to be reliable and explainable. A hedge fund might be able to act on some just generic signal, but we have to be able to explain to the public why the forecast says what it does. Um, Also, technically speaking, AI techniques are very much GPU bound, but the existing supercomputer infrastructure purchased for, or leased for $500 million about 7 years ago is very heavily CPU based. We have a very limited budget for new hiring and infrastructure, particularly in the short term. So our overall plan has to be a gradual adjustment of our work to the AI future as it develops rather than a massive expansion. That being said, if anyone in the audience has an inside track on a meeting with Mark Carney, please let me know. I'd love to have his ear for about 20 minutes. Okay, so to that end, we have ECCC has adopted the so-called AI roadmap. This was written in fall 2023 with a cross-disciplinary internal team of researchers and managers to set out how the science and technology branch and how MSc should essentially think about AI going forward. This was adopted at the directorate level between ASTD and the Meteorological Service of Canada, and it was fully published last summer on canada.ca. I think you can find it with Google, and if these slides get distributed, there's a link in the references. Okay. The overall intent of this AI roadmap is to include machine learning as and where appropriate through the whole forecast chain, from everywhere from data collection to the final generation of expert products like how the watches and warnings get issued. And to that end, there's a three-way evaluation of essentially every ML-related proposal. The first axis is feasibility of is this project not just achievable, but achievable with a reasonable allocation of human and computational resources, particularly since AI is using GPUs, which are scarce, and machine learning expertise, which is scarce. This is sadly a lot more constraining than I, as a researcher, would like it to be. The second question is added service value. Does this project, in fact, better the status quo, or is it some kind of prestige or highly speculative project that isn't likely to pay off? And the final axis is the added value from an energy or cost perspective. Does this project propose an improvement with some advantage of computational time or energy cost or computational cost? The big selling point of machine learning based forecasts is that they essentially run two-ish orders of magnitude faster than the classical systems, and that's really good. And to the extent we can have those results, we would be eager to jump on them. But it's also possible to have AI models that suck up training time endlessly and provide marginal improvements. So this criterion is uh, limits the project selection. The overall intent of the plan is to see machine learning as a routine tool for scientific use by 2030, with increasing adoption up to that deadline, along with the earliest projects that have become operational already. Um, per these goals, like I said, some of these projects have become operational. Uh, we intend to embrace, extend, and then innovate in a sense. The first aspect here is to adopt essentially the state of the art data driven forecasting system in a way that the intellectual property is, in fact, useful for us as a government entity. Then we want to use these data-driven forecasts to, in particular, steer large scales of the current global model to preserve physical plausibility and dense output so that we can take these AI models, even with all their limits, and use them to improve services to Canadians. And then finally, we're looking to develop these models going forward to improve sharpness, to make them just simply better, and to just train models that are competitive with and advance the state of the art. Now, as a researcher, this is a lovely, lovely topic because it's greenfield research and development. There's so many areas where we can progress, and we can progress rather quickly. And at the same time, there are relatively few dependencies on existing forecast systems or and existing users and downstream impacts. There's no question about whether or not we can, say, adopt a change to a model because, I don't know, a secondary air quality forecast might depend on the existing behavior. And that means in the short to medium term, some of this is likely to have off-cycle operationalization when the forecast improvements are significant. And this has already happened to some extent. So the first aspect of this is the adoption of AI models, and this is GEML, or the Global Environmental Emulator. The first model releases came out of the private sector companies, and that left us in a really awkward spot intellectual property wise. GraphCast, for example, has open source code that's freely usable, but the set of weights has a non-commercial license, and that made Environment Canada's lawyers really antsy about what that might mean for cost recovery agreements, because we provide certain services on a cost recovery agreement, but if those forecasts are then based on a non-commercial clause, we just didn't want to be the first government sued by Google because that seemed like really bad press. At the same time, this caused a small paradox for machine learning research and development, because on the operational side, there's no point in adopting anything less than the current state of the art. But on the research side, it's only a really viable research question if you're advancing the state of the art. Take the literature for what it is and do something new. So, in some sense, the research couldn't quite justify just replicating the state of the art, and the development couldn't really advance without it. So, the solution took some dedication and cooperation across the research and development teams, where CCMEP, the Canadian Centre for Meteorological and Environmental Prediction, got dedicated GPU time on our supercomputer to retrain a version of GraphCast from scratch that was using training code that had been independently created for ongoing research projects. And I'm taking speaker's privilege to advertise the talk later this session by Miguel, who will discuss this in quite a bit more detail. And we expect a technical report to come out later this summer. Okay, so that existing now, it's still not exactly great for just straight up deployment as a forecast system. The outputs of a GraphCast or Pangu weather-like system are just too restricted. There's a limited number of variables, levels, and outputs. An airport needs a weather forecast with 5-minute accuracy, for example, but these forecast systems typically provide 6-hourly outputs. It's just too coarse to replace or even meaningfully augment so many uses of the existing forecast systems. In addition, every state-of-the-art deterministic model is greatly smoothing, so the effective resolution is much worse than the grid resolution. And some of the research literature says that there's questionable physical consistency, such as winds that don't balance the gradient of geopotential, particularly at the fine scales. Our solution to that has been hybridization via spectral nudging, which borrows a technique from climate downscaling and regional forecasting, where we take the large scales from an outer model, in this case an AI model that's GraphCast-based GML, and then we use it to pilot the classical forecast based on the traditional numerical weather prediction GEM model. The headline picture is this one. At left, we have the control forecast given by the global deterministic prediction system. I think this is a 5-day forecast leading up to Winter Storm Eunice. In the middle, we have the equivalent forecast produced by GraphCast, in this case, the operational model produced by DeepMind. You can see that the large scales between the two models are different, but GraphCast just misses out on so much of the fine scale variability. At right, we have what happens when we use the GraphCast model to pilot the GEM forecast. We regain essentially all of the fine scale variability, but the large scales, which are more accurate in the GraphCast model, resemble that of the GraphCast model. And because this is a hybrid system, we get all of the dense output fields, levels, and times of the GDPS system that's in some sense a drop-in replacement, and we gain the vast majority of the accuracy from the AI model. At left here is a quote-unquote scorecard. The details don't matter too much, but the way to take about this is that the red up arrow is good with the spectral nudging system better, and the blue down arrow, there are a couple of them, is worse with the spectral nudging system is worse. A scorecard that looks like this with a whole lot of really big red up arrows is very well received operationally. Overall, spectral nudging provides a predictability gain of 12 to 36 hours. So a 6-day forecast in this system has the same accuracy as today's 5 to 5.5 day forecast. And that kind of gain is equivalent to a full innovation cycle of 2 to 3 years by not just one team, but every team. This is currently deployed as an experimental system, and I was told just today that we expect the public data availability to be coming later by mid-June or so, with data showing up on Datamart. And this is the world first operationalization of an AI-based system that meets all of the requirements for meteorological use of a global forecast system. There's a preprint with link in the references, and overall, as having been part of this project, I'm extremely proud of what we've accomplished. Now, the root problem of why we need this kind of system is the forecast smoothing. And that's because machine learning models are smart but also dumb. They optimize very precisely for what's encoded in their loss functions. And what we really want are good forecasts that have both high correlation with the future, low bias, and physically unrealistic output. But that's a really complicated goal. And what we really ask for is small root mean squared error. And that tells the model that it wants to produce the best average forecast of the future that it can construct. But average doesn't mean realistic. If I flip a coin, on average, it's 50% heads and 50% tails. But if I flip the coin, it's never landing on its edge like that. So the fix with this is to take mean squared error, which is simple to compute, and then adjust it slightly to break the aspect of it that rewards smoothing unpredictable scales. To do this, and I apologize for the technical discussion here, we use Parseval's theorem, where we take the look at the mean squared error by spherical harmonic mode rather than pointwise. And we separate these modes by total wave number. Again, by Parseval's theorem, when you write this in terms of the power spectral densities, and you can add it in terms of the paraspectral density difference between a prediction and the analysis and a coherence term, which is the per wave number correlation, you get something that is exactly equivalent to mean squared error. But that second term there, the root power spectral density of prediction times analysis, means that if you don't predict a scale, then you don't have any penalty from mispredicting it. So that's bad, and then we change it. Instead of taking the square root of one of the paraspectral density of one times the other, we just take the maximum of the two. It's a really simple change as long as you have a fast spherical harmonic transform, which is pretty easy in a global model. And the effect of using this to fine tune a global model is pretty profound. The example here is Hurricane Ian, where this is the analysis closest just before the hurricane makes landfall around the time of its maximum intensity. This is and the test case here is the pre-trained 13-level GraphCast model. So this first picture is the analysis of the quote-unquote ground truth. This is the prediction from the control model, the Google DeepMind GraphCast operational model. The location is pretty good for a 5-day prediction, but the accuracy is terrible. The hurricane low is underpredicted, and the 10-meter wind speed is dramatically underpredicted. When you just take that model and you fine tune it with the adjusted mean squared error function, the prediction accurate the location stays about the same, but the hurricane becomes much stronger. You restored the low, and there's a dramatic improvement to not just this prediction, but the prediction of hurricane intensities systematically, and the effective resolution of the forecast comes much closer to the grid resolution. Okay. Finally, I'll introduce parity a little bit because our medium and long-term goal at ECCC is to move past these kinds of small extensions to models and compete in the really big leagues with a new model architecture that um, can really advance the state of the art. Now, new models are large projects, and Parity is made by both ECCC and the Weather Alliance Consortium, which includes several Canadian universities and private sector partners. And the idea here is to have a data-driven model architecture that's physically inspired with a dedicated semi-Lagrangian advection layer that specifically transports information around the globe without trying to backfit it into diffusion-like behaviors of existing systems. This system showing promising results at low resolution with intermediate and high resolution tests pending GPU resources. And I point to the upcoming presentation by Dacres for a lot more detail about this. Okay. Now, finally, I'll talk about the trends in data-driven weather forecasting, both at ECCC and elsewhere. Every weather center with an appropriate budget is looking at AI-based weather projects. ECMWF is probably the world leader in this with a considerable amount of funding thanks to their Destination Earth initiative. But there's also a lot of interest still from the private sector. DeepMind, NVIDIA, Huawei have contributed to the earliest wave of AI weather forecasting. At least some interest remains there. Allegedly, even hedge funds are starting to look at these kinds of models to see if they can, I don't know, pick up pennies in front of the steamroll on the stock market. But if you look at recently published literature and conference talks, a few broad trends are evident. The first one of these is direct generation of forecast ensembles. There's early work here with GenCast, a CRPS-based AI forecasting system from ECMWF, and a group that has trained a model ensemble by retraining a model over and over and over again to get notionally independent members. And the idea is that deterministic predictability of the atmosphere is very limited beyond about 3 days, and you need ensembles to look at a probability distribution of the future beyond that. This is attractive because if these weather models produce individual forecasts 2 orders of magnitude faster than the current system, you can have an order 100 member ensemble for the same amount of computing time as the current system. And that allows you to really explore the tails of the distributions. Now, the trick is that good ensemble forecast systems must be well calibrated, and that's difficult to ensure during model training, and that's something that all these groups are looking at. The next trend is learning directly from data. The main headline forecast systems to date mimic a physics-based analysis, but these systems are imperfect. They're limited in terms of having their own grid resolution and their selection of variables they assimilate, and they're also expensive. So if a data-driven system can learn directly from observation, then it can skip this relatively expensive part of the forecast system and potentially deliver additional value without needing to, like higher resolution or assimilating new kinds of data, without needing to expensively update an underlying analysis system. There are a couple of works here. Yuval 2024 trained the hybrid neural GCM model to match precipitation observations derived from satellite, and McNally and Alex have both looked at full observation to observation mapping without an analysis model in between. For example, taking one set of satellite imagery and trying to produce the next set. Now, there's still lots of work to do, including robust and standardized verification methodologies, because without a forecast grid, you can't really do gridded evaluation. But again, it's a promising area. Okay. Now, as a broad conclusion, AI and machine learning systems are quote unquote coming for numerical weather prediction. They are already showing improvements in forecast accuracy and computational efficiency that are too significant to ignore. A weather center really can't put its head in the sand and pretend that this isn't happening. Now, the field still has serious limitations that mean that we also can't jump on it like the press releases might want. The most important of these is that these forecast systems do produce limited outputs, and getting around that is a major area of research. They have problems with physical consistency because they're not physically based models, and there are only tenuous connections between, for example, global, regional, and local forecasts, because so far most of this development has focused on one aspect at a time rather than interconnections between them. Now, this field promises an incredible expansion of numerical weather prediction services in the future with more local, more accurate, and more timely forecasts, but that is not going to arrive without researchers expanding the frontier in essentially every area of this. Now, what does this look like? There are two schools of thought. The AI booster argument, emphasized by a paper by Bauer last year, is that AI algorithms are a qualitative leap in the way we understand the Earth system, and there are no limits when we learn directly from observations. So this paper and the advocates argue that AI numerical weather prediction will replace essentially all traditional weather prediction in short order, and that means that one or two global weather centers will act as clearinghouses for huge amounts of data, and they'll be the only ones really capable of running models. Another argument is that AI models will augment, but not entirely replace traditional numerical weather processing. The argument here is based on the observation that we only really have one Earth, and we get new weather at the rate of about 1 day per day. So we don't really have boundless amounts of data. Uh, Even though we might be able to learn directly from data, there will be, for a long time, value in uh, creating, for example, simulated data from physics based systems, or using AI to accelerate physics based NWP. But it seems from this argument unlikely that it will be able to make a AI based numerical weather prediction will be able to make a truly transformational leap independently of the physics-based systems. But regardless, the genie isn't going back into the bottle. I don't foresee a future where 5 years from now we come back and say this AI was a terrible idea. And finally, I'd like to end on a sober note about the ethics of AI numerical weather prediction. Uh, AI is a really fun computational problem, but lives and property really depend on accurate weather. Improved forecasts save people's lives. Predicting a blizzard a day ahead of time will mean that some people will not get caught on the road and frankly killed in car accidents. But a forecast bust can also get people killed for the same reason. It makes it an extremely complicated ethical landscape that we all must pay attention to. On one hand, it means it's irresponsible to disregard real improvements to numerical weather prediction out of an aesthetic distaste for AI. But on the other hand, it means that we need to work on explainable models because black box models are not necessarily trustworthy. And it means that a problem once observed might happen again without being able to fix it. We also must be careful about biased or limited data. My go-to example here is that a model that predicts tornadoes based on Doppler weather stations might learn that tornadoes only show up near cities likely to have Doppler weather stations. And finally, traditional public sector weather centers really need to take a considered and cautious approach to these innovations, no matter the source. And I don't have answers here, only lots of questions that I hope this field can tackle in the future. Thank you very much. I have references here. Like I said, I hope these slides can get distributed, and I'm happy to take questions.
Thank you, Christopher, for this very extensive talk. Are there any questions in the room here? If not, you end with a lot of questions. I have one for you, Chris.
Mhm.
There are a lot of models that are being released every 2 months in the last 2 years. Usually, we knew the performances of ECMWF, NOAA, and other major centers through the world. Now, how do you assess the performance of this model, given that there are so many releases, and choose one and evaluate them? So, what are your thoughts on that?
My thought is somewhat cynical in that I think so many of these models are being released for press release considerations um, rather than considerations related to operational weather forecasting. Uh, So, a model release by a research group is a research project. That doesn't necessarily mean it's ready operationally. But at the same time, since there are so many being released that are pushing the frontier incrementally, it doesn't necessarily matter a whole lot right now what model a weather center settles on. GraphCast was first released in the second half of 2023, and it is still, for all intents and purposes, a state-of-the-art model. I think AIFS beats it slightly on some scores, but in terms of how rapidly AI has advanced, I don't think it's necessarily a slam dunk decision to use one or the other. Um, so and also just as an operational weather center, a model must be trusted before it's deployed. And if it takes time to gain that trust, then that is time that is well spent. Um, we shouldn't operationally be chasing the latest fad in anything. Um, and research-wise, I mean, um, researchers have always had a problem with figuring out and chasing the state of the art. And speaking as a researcher myself, it's very tempting. And this is going to come down in part to the practices of open science and whether or not these model developers make their code publicly available, easy for others to use and extend, and whether their papers are frankly well written enough to understand what's been done.
Thank you, Christopher, for that. Yeah. Yeah, I'll bring you the microphone.
Hi, Chris. Thanks for the talk. I was very interested in the approach using the AI-generated forecasts to guide the NWP models with the spectral nudging. And
Yes.
my question is, how do you decide on what scales you're going to nudge towards the AI-generated fields, and where are you going to let the NWP generate its own event?
In this particular case, our decision was mostly based on which scales the controlling model reproduced without too much variance loss. If I remember correctly, the cutoff wave number or the cutoff scale for this implementation was about 2,500 kilometers, because much shorter than that, and the controlling GraphCast forecast starts losing more than 10% of the variance, and that just made the forecast too underactive. Um, it is a delicate question, and there's room for optimization because for you want to capture as many scales that the model predicts more accurately, but you don't want to you don't want to include scales that are just better because they're smoothed. Um, so the 2,500-ish kilometer cutoff and 6-hour nudging interval worked in this case, but there is some interest in figuring out how we can potentially apply this at higher resolution at hourly time scales and include this inside the data assimilation system, for example. But that will depend on figuring out and characterizing how to make an outer AI model sharp at these scales and these lead times.
And there aren't any concerns about artifacts associated with upscale propagation of information?
Surprisingly, no. We were looking for it, and we haven't seen any yet. Now, it is running experimentally. The forecasters are looking at these outputs as they're available, and we'll be. We hope we don't see any bad reports from them, but if we do, we'll take a look at it. Um, I think the intuition is that the finer scales evolve relatively um, freely by themselves, but constrained by the larger scales, and the upscale propagation with the strength of nudging we're using is not constrained too much. And if the outer scales are more accurate, then the upscale propagation from the fine scales should be consistent with that anyway. So it may very well be just a divine coincidence.
Thank you, Christopher. That's all the time that we have. So one last round of applause for Chris. Thanks for this good overview of what we do at ECCC. Now I'm getting back to my station. Now, let me introduce you, Anne Dacres, who's working at ECCC and who's the coordinator at the AI integration unit. So Anne?
Yes, thank you for attending. So I'm just going to check to see if I'm muting this properly. Of course not. What did I just do? Did I turn it off? There we go. Okay, too many buttons. Okay, so and Dacres, but I don't work alone. You see 2 robots there? This is the second robot. We're in the development of expertise unit, which is a very new unit. And I just wanted to take a moment to place it because we're really working with the design and integration of numerical forecast systems in AI, very much with the numerical weather and environmental systems, prediction systems. So a bit less on the services side, even though we'd love to be helping them. We do what we can, but we're focusing a lot on our modeling colleagues. So a bit of context. Christopher has already mentioned a few of these points, so I'm not going to go through them all in a lot of detail, but like machine learning has been used at ECC for a long time. Researchers have been integrating it into their modeling and testing and so forth. But it was really late in 2022 when generative AI used in certain large language models that you've probably heard of exploded, became more mainstream. And almost at the same time, around Christmas of 2022, if I'm not mistaken, forecasting models integrating AI became the buzzword. So GraphCast, in case anyone was wondering which one, followed by many right after that. So of course, this was very exciting. And our upper management was very interested in what was going on as well. So Miguel and I were in the training division at that time, and we were asked to get a little more involved on how we could start looking at AI to prepare the workforce. So in the fall of 2023, as Christopher mentioned, ECCC developed the roadmap. Our unit was created following that roadmap. It was part of the plan. And then we developed a training and outreach plan for MSc and other colleagues working in atmospheric and environmental science. So how did we do this? It was a big ask and we had little time. So training needs analysis, surveys. So in the fall of 2023 into the winter of 2024, we asked our colleagues, well, what are your views on AI? We're like, where are we starting from? Are you against it? Are you scared? Are you excited? So that was a really interesting exercise to see how they were feeling about it at that time. We wanted to know what experience they had. Had you studied it in university, maybe 1 or 2 courses, or perhaps you've tried to integrate it into some of your everyday work. And we also wanted to provide management with a high-level view of their current skills, but also their expectations towards management. You know, we're hearing about all these new AI tools and models, like where do you stand? So, and with respect to training, which is what we really wanted to see, the results were all over the place. So there were some people who were just starting out, who had just read a few articles and who wanted to get a good foundation in AI, and others, as I mentioned earlier, were already using it. So where everyone agreed was that they wanted training. So they were even saying, we want like 2 weeks, that's fine, we're ready to invest our time. This is a subject that interests us. It was also important for us to support the roadmap, of course. So in the roadmap, there's training and communication, and this is where we come and support the roadmap with what we do. So in terms of training, baseline. So we work for the Government of Canada. There are policies and directives in place that we have to respect. So yes, there's that, and I have to put it up there. You'll see in a moment, though, that I want to congratulate the Canada School of Public Service. They're doing a great job. And we also felt that we needed to create a foundational course, so really an AI 101. And this would be for everyone. So some people had just been playing around with AI and knew very specific parts of it or tools. So we wanted to really offer a foundation. So this is where I'm congratulating the Canada School of the Public Service. They've evolved really quickly, actually. So from a few courses at the beginning to now, a whole learning path for people who are interested in learning more about AI, not only about their policies, but actually learning how to use AI. So it's really interesting, AI and data. AI 101, that's the course that I was talking about. And we actually today finished our last cohort of the season. We've offered this course to 6 cohorts so far. Oh. You can still see. I'm gonna continue talking because I'm stressed out that I'm gonna go over my time. So we worked with Evado. Evado is a consortium based out of Montreal that brings together NGOs, academia, and governmental institutions to, no problem, to basically promote AI, to share resources, to promote learning as well. So they were an ideal partner to help us develop this course. So basically, we provided an SME, a subject matter expert. So one of our researchers who'd been using AI for a while, and he helped the instructor tailor this course to ECCC scientists. So basically, what we wanted from an organizational point of view was to enhance the understanding of projects that were currently being done at ECC, because our researchers would come to present, and we had all kinds of specialists. We had meteorologists, we had computer scientists, but the AI jargon was new to many, many people. So let's get everyone on board. We wanted to help them recognize the potential of AI in their own projects. And we wanted to enable communication and collaboration within the department. So I think I said some of these things. Duration might be of interest. We settled on two-hour workshop for 3 weeks in a row. So for a total of 6 hours. So we just touched on it, but it was long enough for people to be able to ask questions and to get a good idea. It was offered to basically all of the service. And also, should I stop?
Forgive me, your
That's
slides
okay.
aren't showing online, so I just need to make an adjustment here for you.
Perfect, thank you.
This is not yours, right?
Yes,
This one is yours? Okay.
yeah. Apologies to the folks online. They weren't seeing my slides.
So you need to hit this button. Okay, window. Here's. That's not the whole slideshow, right? And so give it 30 seconds and then, oh, this is not my phone.
Perfect. So yes, 6 hours. The target audience, at first we thought, well, we'll see who's interested within MSc, but we had people coming from science and technology who were interested. We had people, from the operations side of things that were interested. So the demand kept growing and growing, so we suddenly ran into a really long waiting list for people who wanted to take this course. So we've expanded and we're offering 4 more cohorts this autumn. So I think we've made a few people happy with that. And what's interesting as well is that a lot of the managers signed on as well. They wanted to be able to communicate more clearly and understand, to be able to plan for the future.
Speak into the mic and say, I need tech support. These guys will magically appear.
I'm okay? Yep. So just to give you an idea, of how these sessions were divided up. Foundations of AI. This was what our instructor called eating the spinach. So it was basically a review of data use and how AI. I have 3 minutes left. 5. Okay. AI and AI integration going into machine learning, deep learning. And then we had practical applications of AI at ECCC, which is where our subject matter expert came in and provided case studies so that people could really connect to what the instructor was saying and see how it was being applied within our teams. So managers, I'm gonna have to go fast, guys, I'm sorry. We didn't forget them. Ivado has a community of practice. Miguel is on it. They offered a great day where they brought together people from all fields to discuss change management. So how is AI being integrated into these organizations? What are their challenges? And most importantly, what are the solutions? So not necessarily surprising results, but really fruitful discussions, I'd say, and good connections as well. Other AI. So yes, this is what started the ball. So we do training, but we also try to promote knowledge sharing. So early in the fall of 2023, when all of this was coming together, we actually held 3 days of seminars. So as you can see, day 1 was really all the weather centers. What were they internationally? What were they thinking? Where were they going? Was AI even on their work plan yet? Private sector all came. As you can see, there was a lot of interesting people who were there to present their projects. And then internally, basically, what we were doing internally in terms of research, development, and infrastructure. we came to the CMOS conference last year. I promised Serge that I would call out to him, and I will, because GraphCast had come in December, just before Christmas. And in January, when we came back, we contacted Serge and we said, I know it's too late, but can we still try to get a session in for the next CMOS? And he made the magic happen. I don't know how, but he got a session added for us. So thank you very much for that. So we're here today for the third session, and we try to go to different sessions to network and so forth. I think maybe this is the last really interesting one, is that we have a really good partnership with our training division. So we hold webinars, and we now have an AI series. So they allowed us to come in and basically showcase what we're doing internally, but we also get to invite external guests as well. So it's a really interesting tool for us. So I think next steps, AI 102 for the coders who are saying, I like all this theory, but how am I actually going to do this? And more advanced AI training for ECCC, the people who are actually doing the research and development. So it's basically going to be in-house training on our own tools. I think that's it, Miguel. Did I go fast enough?
Yes. Thank you. Thank you. Any questions for Anne? If not, let me throw you a curveball. So I saw that you and your team did a lot in the last few years. So how do you assess the success or the fact that what you've done is actually hit the target?
Well, I think maybe because we're a small team and we took the time to think it through, I feel that we didn't necessarily spread out very much, but we did what we could based on the needs that we saw. So I think where we targeted, like the AI 101, I feel is a success. I didn't talk about a forum, but we have an AI for all forum, and there's activity on that forum every day. And the Stay Connected, I think also is we have some good stats, let's put it that way. We have a lot of people attending those webinars. Yeah, so I'm proud of us.
Thank you, and last round of applause for Anne. Merci. And sorry for the technical hiccup. And now, let's welcome Professor Raymond Spiteri, who's from University of Saskatchewan, that will explain us PARADIS.
Hello, and thank you, everyone. So thanks to Miguel for the invitation to attend and speak with you, and thanks to those who are in the audience, both live and virtually. Okay, so
That's right.
okay, which button is which? Do you
It's
know?
the side button.
This one here?
To the other one.
This one. Okay, very good. Okay, we're off and running. Okay, I usually like to start. So I'm Raymond Spiteri. Let's try this again. Oops. Uh-oh. Okay. I'll quit while I'm ahead. I'm Raymond Spiteri from the Department of Computer Science here at the University of Saskatchewan. So I work closely with ECCC on some of these AI-related things. I'm going to talk to you today about PARADIS in particular. I've got some names of other people that I collaborate with, in particular Stéphane Gaudreau, but also Carlos Pereira, my former PhD student Siki Wei, and Chris, who gave a wonderful presentation to kick us off. So a few disclaimers. I'm not an ECCC person. I'm not really even an AI person. I'm sort of an old numerical analyst. I try to keep the people honest in terms of, you know, AI can be really viewed as applied mathematics in its extreme in some sense. And so there's a lot of things that, you know, oh yes, we're familiar with that. We've done that before. It's just called something different, right? So this loss function thing, we used to call an objective function. It hasn't changed, but you have to learn a new language, but that's okay. It keeps us all young. So I really wanted to make a bit of an advertisement about the Weather Alliance Consortium that we're building between 9 universities, and we have ECCC and a number of other partner organizations that are going to help us somehow democratize the weather forecasting business, so to improve it and to make it more accessible to the public. We are believers that, AI-driven, like data-driven models, as Chris was saying, they have their issues. I'll talk about them again quickly. We did not share slides, or we did not consult ahead of time, so these are sort of independent thoughts in a way, but they are similar. We do share perspectives. The issues are that, it seems like we have very much, history and success with physics-based models, and I don't see how one model is going to win completely and decisively over another. I think the optimum is going to be a hybrid of the two, to a greater or lesser degree, although it's not guaranteed to be 50-50, but there will be some sweet spot in which, we get what we want. So here is the long list of academic institutions, including University of Saskatchewan and all the different partner organizations that are involved. So there are going to be a couple of scary slides here. I'll warn you in advance, but I figure that the slides will be made public, I hope, and you can then take your time to stare at whatever slide you want for as long as you want. So quickly, just some background, and I'll talk about PARADIS quickly and some of the preliminary results. Chris has foreshadowed some of them, but not all. Okay, we know that accurate weather forecasting has essentially made a very good point. It matters. It's not just a fun exercise. Here's one of the scary slides. So we are solving equations, and they look like this, and they kind of scare me too. So I mean, I can imagine how the general person might feel about it. Often what I do is I get the equations printed on a t-shirt, and then I wear the t-shirt so that way you can stare at them if you don't want to listen to everything else. The issue behind these things is that they look scary and they look like they should be able to describe whatever you want, but the truth is they don't. Modeling is a very difficult thing. All models are wrong, but some are useful. So the issues here is that we only have partial knowledge. Even if we could solve all these things exactly, we're going to be missing stuff. And essentially, my philosophy is, well, that's where the AI comes in. It helps us fill in the blanks in an easy and reliable way. So you've seen some nice pictures. So here we are. The state-of-the-art weather forecasting does a reasonable job. I think it's kind of like 80% of the result with 20% of the effort, frankly, right now. But 80% is not good enough for what we want to do. Some of the challenges that people sometimes do or don't talk about, like training is expensive. They talk about, oh, this is very cheap to make forecasting. I can make a forecast of the next day in an hour after you've done, 2 months of training. The black box nature that Chris alluded to is we like to understand where the predictions come from. We just can't take the answer at face value. We've seen some over smoothing that Chris showed in his graphs. The physical consistency is a problem. You can get you get sort of negative pressures or negative densities, things that can't happen physically. When you're talking about extreme events, I mean, how much confidence do we have we can predict something we've never seen before, or with an AI model? And how can we need to be able to trust them so that, if and when, or just maybe when things go wrong, we can somehow understand and, being able to trust the forecast. Already there's issues with forecasts, even as now people, you don't want to evacuate, et cetera. So there's all kinds of issues around that. The new model that we're working on with ECCC is called PARADIS, and there was the theory that we wanted, a nice name and then tried to reverse engineer the words to go with it. There's nothing wrong with that. They're not for those, so the advection diffusion reaction physics underneath, which I'll talk about really quickly, comes out of this paper from, that was in NIPS a couple of years ago, or actually this says 2025, but that's not quite right, I don't think. These are not, for those of you who may know something about it, these are not what are called physics-informed neural networks. I'm a fan of physics-informed neural networks, so we're going to have to see how much we'll need to introduce that kind of technology into this. So quickly, we're dealing with what are called convolutional neural networks, which are a special kind of neural network that basically is made up of layers. I didn't bother to try to draw a picture of it, but basically they learn represent the data. And it's analogous, again, for those of you who know how to solve partial differential equations. You build stencils and you solve equations that way. So the sort of the claim to fame here is that we're trying to replace the differential equation with a neural network. That's kind of the essence of it. But we want to do it in such a way that the neural network still operates in a physical way. Okay, so that's kind of the key. It's a little subtle here, but with a lot of the details behind, well, the neural network will just somehow learn what it's supposed to do if you give it the right ingredients. So these convolutional neural networks, we blame them for the over-smoothing. They can't do a good job when you want to move information over long distances and not have it deform, okay? So if you want to move imagine the little gray square has a little picture in it and you want to move that picture from one corner of the grid to the other, you find it doesn't work very well. So what we wanted to do is we wanted to introduce more of a transport component. So there's a transport PDE, if you will, like a wave equation. We want to introduce that into the architecture. So we fall back on doing something called advection, diffusion, and reaction, because those are the kind of underlying processes in the atmosphere. We're taking advection as a separate element from diffusion and reaction, and then we apply integration in time. So my background is time integration, and so I'm right now tasked with some kind of like poking around with the architecture that exists to see if we can get better results and get them faster by introducing or applying stuff that we already know from numerical analysis. So again, more equations in the sense of we have diffusion and reaction and characteristic equations to represent transport. And then we translate that into what is called a latent space, which is kind of where the neural network operates. And then we use the semi-Lagrangian approach, which is this advection. You can think of it as almost as like using particles. And then we do the integration of the diffusion and the reaction. And then we we come out of that latent space back to the real space and get a real prediction. Okay, so here's again kind of what things look like. Again, it's a technical detail. It's called the method of characteristics because we're assuming that things get transported without deformation. So if we're trying to figure out a prediction for a spot in the future, we say, okay, where did that spot come from in the past? Because we know that, and then we simply translate it. Okay, so PARADIS is giving good results. So these are even older. These are the first results that came out from PARADIS. I think Chris probably has better results now, but you can already see that this is pretty good, right? So compare this, so the PARADIS simulation is on the left, the real data are on the right, and you can see this is not bad, and there's really not a lot of smoothing in there. These are 1 degree resolution, and here's, so what's this? This is the GZ 500, so the pressure at 500 meters, I think. Again, not the meteorologist, so I don't know all these things necessarily off the top of my head. Again, if you look at the pictures, they look pretty good. They aren't, I guess, accurate enough for operational purposes, but we're getting there, and this is pretty good. This is a we're very encouraged by these results, shall we say. Here's a similar one for total precipitation. Again, similar comments. And finally, here's a comparison against GraphCast and essentially how we're doing better in terms of the errors are still there, but they are lower in general and less widespread. Okay, so I'll leave you with the conclusion that we are building a Weather Forecasting Alliance Consortium, and we still welcome collaborators. We're going to be applying through the NSERC Alliance Society program in order to get some funding, and again, we have a lot of excellent members on our team. Our goal is to increase weather forecasting accuracy and accessibility by combining physics-based and data-driven approaches. We're all encouraged by the preliminary results from the physically inspired PARADIS model, and with people like Miguel and Chris on our team, we're very optimistic that we'll be able to do something great in the future. So thanks for your attention.
Thank you. Any question here or online for Dr. Spiteri? If not, oh, yeah, I'm coming.
Yeah, very interesting talk. Just a quick question about the data for this model. Like you are comparing it against ERA 5, right?
Yeah.
What is the input? Like
Sorry, what
input you are using for this model? In terms of the state variables, like to initialize and all that stuff.
So which variables are we modeling?
Yeah, like no, which data you are using? for this machine?
ERA5 data.
So you are using ERA 5.
Yes.
That's what's going into the model.
Yes.
And then you are comparing it against ERA 5. Like that's what I'm trying to understand.
Yes. So then we make a prediction. Of course, the prediction doesn't know about the ERA5
So you are using ERA 5 prediction to compare your prediction, right?
Well, we're using the measurements, from it.
Okay.
Yeah. Does that make sense? Like we're using it to, we're using it to build and train the model.
Okay.
And then we make a prediction, and then we compare that against
ERA 5 prediction.
Somehow, yes.
Okay.
Yeah.
Okay. Now I think now I understand.
Sorry, I think I misunderstood you.
ERA 5 is an analysis, it's not a prediction. So you compare with the ground truth, which would be ERA 5 as well.
Yeah.
No. ERA 5 is analysis of Oh, well.
Yeah, you don't use the future values in the training, so it's valid. You pretend you don't know it. Yeah.
Thank you. Any other question? Anything online, Anne?
I had something online, but Christopher came in and saved the day.
Oh, okay, fair enough then.
If I have a question for you,
Sure.
though. You have a pretty impressive team with a lot of people around the table. So I was wondering how you assign or tell to every member of the team on which part of the problem or equation they will work on. How do you split the work around the people?
Okay, so ideally, people kind of volunteer for things, right? So I'm a big fan of, people should be enthusiastic, right? So which problem are you most excited about? We'll give you that one because we have more problems than we can solve. So we sort of lay them all out there. Now, different problems have different priorities, and different team players will say, I'm going to work on this problem because it's a team priority. And some people say, well, I really am interested in solving this problem. And so it just somehow all manages to work. And that might be an effect of being understaffed, right? So, yes.
All right. Well, thanks again, Mr. Spiteri.
Right. Wonderful. Thank you.
Yeah, I need the paper though. She's coming. So we have the honor of having Parvin Ghaffarian, who's going to present enhanced short-term forecasting of meteorological variables using stepwise regression, a case study of the Kzno Lake Basin. I don't have her short bio, but I know for a fact that she's at the University of
UNBC.
Yeah, UNBC. I always get mixed up with acronyms, but Northern British Columbia. So
Thank you so much.
welcome. Thanks for being here.
Hello, everyone. My name is Parvin. I'm a meteorologist and research associate at UNBC. I'm using traditional numerical weather prediction for simulating weather parameters over Kzno Basin that has very complex topography, but using an NWP model over complex topography is challenging and time-consuming. I decided to work parallel with AI and compare the result with the NWP model. In this study, I used a multivariate, multi-step model forecast for predicting atmospheric phenomena over Kzno Lake Basin. Accurate short-term weather forecasting is critical for disaster management, agriculture, and energy distribution. When I talk about short-term weather forecasting, I mean nowcasting. Nowcasting is about 50 minutes forecast up to 6 hours. It's important for aviation and for forecasting convective storms, for example, tornadoes. And traditional numerical models often struggle in complex terrain due to computational limits and local variability. The Kzno Lake Basin presents unique forecasting challenge due to its steep topography and microclimates. AI offers powerful tools to improve forecasting accuracy by learning complex nonlinear patterns from large data sets. Integrating AI with statistical methods like stepwise regression enhances both performance and interpretability. The study area is over Kzno Lake Basin. This picture shows the slope over this basin. The green shade shows the flat area, and dark brown shows very steep area. As you can see, in some area, a slope exceeds more than 80% degree. And due to this steep slope, and also due to updraft, very strong updraft, we encountered very challenges to using NWP model for forecasting or simulating atmospheric weather parameters in this area. And also, you can see the lake. The Kzno Lake is a fjord lake or glacier lake, and the maximum depth is about 500 meters. It can claim that is the biggest fjord lake in the world, and the biggest and the deepest lake in BC, and the third biggest deepest lake in North America. And our research objectives is it's improve short-term forecast of some meteorological parameters, for example, air temperature and relative humidity and atmospheric pressure. And we use a stepwise regression model to enhance accuracy and interpretability. And also we compare performance with AI models, for example, AAN, XGBoost, that's relatively complex, and decision trees to demonstrate practical value. For this reason, we use the observation data from the Kzno Research River Center, Kzno River Research Center, QRRC. We choose this station because the weather station is positioned at the 10 meter and no need to use the roughness length to converting wind to 10 meter height. And the period we choose from January 2018 to December 2021, and every 50 minutes we have the data. After cleaning, we had 23,403 records after cleaning, and input features were temperature, relative humidity, and sea surface pressure from 3 previous time steps, T-2, T-1, and T. And our target is for 5 time steps, T+1 to T+5 for each variable, and the interval between these steps is 50 minutes. And we use data splitting. Last 1,000 records considered as external validation set, and the remaining records divided to 2 sections. 70% we use for training set, and 30% for testing set. Here you can see the model architecture of our research. The stepwise regression is fundamentally a statistical technique, and it automatically selecting variables and features and use them for predict values. Here we have only one vector, and in this vector you can see three parameters. T denotes temperature, H denotes relative humidity, and P denotes atmospheric pressure or sea level pressure. And also we have 15 models, independent 15 models as predictive models. For example, MT sub T plus 1 indicates that model for predicting temperature at the step of T plus 1. And after that, we can have the predicted value of 3 parameters for 5 steps. Here, this picture shows air temperature for 5-step prediction related to interpolation test. We selected 200 records by chance, and the aims was the comparing the predicted value with the observation value. As you can see here, for air temperature, there is a good compatible between observed and predicted value. And with in time step 5, as you can see, the RMS value is higher compared to step number 1. And this picture shows the time series of air temperature for 5 steps. As you can see, at the first time step, there is a good agreement between observation value and the predicted value by in the 5 time step, there is a significant difference between observed and predicted value. And also for atmospheric pressure, there is a good agreement between observed value and predicted value, and time series also shows these rules. But for relative humidity, there is a significant difference between the observed value and predicted value, even for time step 1, because relative humidity is a complex parameters. It is not independent. It depends on pressure, temperature, humidity. It needs more work to improve the result. And here you can see the time series of related humidity. And also I selected 3 samples for 5 time step to show the observed value and predicted value for time step. You can compare the value of RMSE for air temperature, relative humidity, and air temperature. For air temperature, the RMS value has a lowest amount, and there is a good agreement between the observed value and the predicted value for air temperature. Sample number 2, these are selected by chance, and sample number 3. And here you can see the result of train and test for interpolation of the proposed architecture. As you can see, the amount of RMSE for air temperature in train and test has a lowest value, and for relative humidity, the value is high. And when the time step increase, the amount of errors gradually increase. And this is my favorite slide, because I want to show the regression, a stepwise regression model has a good value for forecasting atmospheric parameters. As you can see here, we use another neural network models. For example, for neural network, we use one layer and narrow, medium, wide, and three decision trees, and also XGBoost 1, 2, shallow and higher depth. As you can see, our model has better result compared to another and has lower amount of errors. Only the XGBoost in higher depth can compatible with our models. And for conclusion, accurate weather forecasting with stepwise regression in the Kzno Lake Basin, temperature forecast showed the highest accuracy, especially at the first time step. Atmospheric pressure prediction remained stable and accurate across all time steps. Relative humidity was more challenging with high error. It needs more work. And another advantage of our work is comparable of higher accuracy and better interpretability, clear insight into variable relationship. And limitation and future work, lower accuracy in humidity forecast. It needs more work, potential improvement using radar or remote sensing data, because recording data over complex terrain and aquatic environment is challenging and not cost-effective. We can fill gaps with radar, remote sensing data, and also reanalysis data. Recommended developing hybrid model combining a stepwise regression with deep learning for extended forecast. And the end, I asked ChatGPT to design an icon for my research, and it created by ChatGPT with this slogan, AI and meteorology better together. Thank you for your attention.
Thank you, Parvin, for this presentation. Are there any questions? Is there any online? No, let me. If not, while Anne is looking online, I have two. Let's start with the first one. So when you were looking at the three variable, are you looking at them correlated together or separately?
Separately.
Okay. So is there something that you might consider to have them all together, since relative humidity might depend of the other?
In the future, we decided to consider all of together. Yes.
Okay, if not, last chance. Yeah, I'm coming.
Just a quick question. You used relative humidity as one of the three variables. Are you using RH as a proxy for precipitation? I would love to see precipitation in mountain areas. It's very difficult to predict. So why didn't you work with precipitation directly?
It's a good idea, but we have automatic weather station over Kzno Lake. There are 7 automatic weather stations, but there is no rain gauge for have the accurate value of the observation precipitation, but we can use satellite data. For example, TR tropical satellite that measure the precipitation. We can use or we can use ERA5 data and input this data to the model for predicting precipitation, and also consider the effect of precipitation and humidity, which are over together.
Thank you, Parvin. We're getting a bit late, but I have a question online, isn't it? And I want to make them. Yeah.
I hope. Why does stepwise regression increase the risk of overfitting in weather prediction models, and what strategies can be used to mitigate the issue?
A stepwise regression Stepwise regression can select the good value only for the training part, but for the real data and new data, we should use cross-validation and also try more to improve the result.
That satisfied me. I hope it satisfied Jeff as well. Thank you very much.
Thank you. Thank you.
So Miguel, the pressure's on you now. We're a little bit late, but last but not least, Miguel Tremblay. He'll be presenting Retraining GraphCast at ECCC, Strategy and Implementation.
So right now I'm the manager of the AI expertise development, but last year I had the chance to manage the team that did the GraphCast retraining. So that means that the people that did the real job are all the other name on this slide. So a little bit of context. So in December 2022, December 24th, I don't know why this seems to be something important that's happening on every year, 2022, 2023, and 2024 on December 24th. So GraphCast, Google DeepMind released a model called GraphCast. And you know that something is going on when your in-laws are sending you article where it talks about model and RMS. So that's what happened. So the results were impressive. We had a look at it. It was fine, but the license were constraining. The code were under Apache 2 license, which means that we can do more or less what we want with that internally, though the weights were under a Creative Commons, paternity, share alike, non-commercial. Do I forget one? No. So basically, you cannot sell anything if you use GraphCast, which is a problem because if we want to use that internally, we have a handful of products that we do some cost recovery. So that was a problem for us. So we started a project to retrain GraphCast. So the main goal was to use internally GraphCast, of course, but also to develop the expertise to train a model internally on GPU, something we hadn't done before. So the end goal was also, once it is done, to distribute the weights under the open government license, which means people from the private sector that you can use it and sell products with no problem at all. Voila, so the main goal were not to outperform, but only to, I'll continue like this. That way, I'll be able to look at the slide at the same time. And it's a little bit lively since it's the last presentation. So just put here. Okay, so the goal was not to outperform. We wanted only to have more or less the same. So the retraining, in fact, was complex because we had to, we only train for a 6-hour forecast using ERA 5, which you've heard before, the golden standard to train this kind of model. And we used ERA 5 because GraphCast was trained on that. That's why we didn't use any Canadian data. We could have used that, but this is not what we wanted to do that. We had a hard deadline, which mean Christmas 2024. Why? Because we used a complete machine, putting everyone else outside this hardware. I'll give you more information a little bit later. And if you had to go through or to do that on your own, if you read the DeepMind, Google DeepMind paper, there are holes in it. There are things that are not said. So once you write the script, you have to make educational guesses. Educated? Yes? You have to guess. So we call this this retrained model GEML. Christopher Subich gave a word about it. It stands for Global Environmental Emulator. This is our own in-house quarter-degree 13 level version of GraphCast. This is what we use for the spectral nudging that Chris described in the first part. the main training, I'll show you different parts a little bit later. We use ERA 5 for reanalysis, but we fine-tune with HRES. So for those that are not familiar with HRES, the HRES is the analysis of the ECMWF global model, not to confuse with the reanalysis of the ECMWF forecast center, which is called ERA 5. So we completed the training in late 2024 using 8 GPUs, A100. The cheap version of these GPUs is 20,000 Canadian dollar each. So we're talking about only for GPUs, anything, no energy, nothing for the rest of the hardware, or more or less between $150,000 and $200,000. This is not cheap. So since it took a lot of times and we only had more or less one try to do it well, we started to train with the 1 degree because it is cheaper. That way, and GraphCast also published a 1 degree model and their weights. And we were able to assess that the script that we use, the way that we use the hardware was a good strategy. And once we were satisfied, we started the 1/4 degree retraining. So, training strategy. There are 4 phases when we do that. So those that are familiar might know those phases. So the first one, this is where, so on batch number that we use on the x-axis, and this is the training loss on the y-axis. So the first one, this is warm-up and stabilization. This is where we train the model and it converged very rapidly. And the second phase, it's long. So you'll see the time on the next one, but this is 200, well, almost 300 batches. I won't say 299 in English, it's too long and complicated. So this is where we use the full ERA 5, and this is where most of the learning of the model happens. And the phase 3, which is pretty short but expensive, it is 11,000 batches. This is, okay, up to phase 1 and phase 2, we only look at 6-hour forecast. This is where we optimize. Starting in phase 3, we look at longer forecasts, 12 every 6 hours up to 72 hours. So we optimize the 6-hour forecast based on the longer result forecasting. And finally, this is the small notch at the end, this is the fine-tuning that we did with HRES. How long did it take? So, the first one, 3 hours. This is the fun part. It converges rapidly and it's fast. The second one, 47 days, continuously. This is done on the development server. So the people on the first slide, they had to be on shift and check when they wake up on the 3-day weekend if anything had stopped. And somewhat along the process, we lost 1 GPU because it simply broke. That took more time. So phase 3, so if you remember, this is the where we train for a longer forecast. Only 19 days, almost 3 weeks. And now we're around Christmas. Luckily, between Christmas and New Year's Eve, not a lot of people use the GPUs. So we extended the usage of the hardware up to January 6th, I think. And we were able, using 24 days. This one, we only did that not on the machine, but on spare time that we borrow here and there on GPUs to do the fine-tuning. So, in short, total training day, 3 months. 1 shot. So, what are the results? We were a bit surprised. So this is a scorecard. The only thing that matters here is that there is a lot of red. Red, this is our own weights compared to GraphCast weights. Our results were significantly better. Okay? That was a surprise for us. And we have some good intuition why this was the result, because the educated guess that we made probably gave that. Though, and this is a constraint that we learned that is very different compared to NWP, is that the training is so costly that all the questions that we had in the meeting during those 3 months, and trust me, we had a lot, we cannot really do experiment to test them. It is too expensive. So next step. So we plan to release the model weights under the Canadian Open Government License in the next, I don't have a specific date, but let's say that by September, all those weights should be available. And I say this in plural because we will release all the steps that occurs during the training, so people will be able to download and see where the some pattern might emerge if they want to do some research. Internally, we will have more GPUs starting this summer, so more experiments. And we had the chance, so my team at the moment had the chance to train new models and, well, see how it works, the decision. We built a relationship with the people in charge of the hardware because they're not used to have GPUs used like that. We have thousands of CPUs, and we're used to use that for NWPs for decades. But GPU, this is pretty new for everyone. So we had some learn. Voila. Combien de temps?
It's 3, but you can.
Okay. So conclusion. Well, as you know, Canada is not for sale. So now with those weights, we are sovereign with this by using this model. And we built an internal capacity, like I said, to use the infrastructure. Collaboration with IT, research, and development team has been put in place. And one thing, high compute cost make openness and reproducibility essential. This was very expensive. This is your taxpayer money, so we'll give it back with weights because we're the government. Private sector do not necessarily do that. When, I don't remember, there were a list of models. Most of them released their weights under a non-commercial license. So they say they're open. Their model are open, not their weights. It's an important constraint. Voila, I'll stop there, I think.
Good place to stop, Miguel.
Merci.
Yes.
Thank you.
Thank you. So I know it's break time, but if anyone's willing to stay, I think Miguel would be willing to take a couple of questions. If not, for those of you who need to leave, I want to thank everyone for attending the session this afternoon. Thank you. Thank you. So I see we already have a question, and Miguel, you have the microphone.
It's handy that I'm just sitting right here. So I actually have 2 questions, but I will only ask one for now. You said one of your GPUs broke down during the training, and you offered a reason why. So if you could maybe repeat that for us. And then the second part is, and did you therefore just run the rest of the computation shorthanded, or what happened there?
Well, it's very interesting. The material were not very supported 24/7 because when we bought a supercomputer, it was in the last era. So GPUs are like a strapontin, it's an add-on. So we had to wait until they figured out what it was, given that they asked for a system time, so stopping everything. We run with 7 GPUs, then they changed the motherboard because this hardware is very expensive. So when a CPU broke, they just replace it. No question asked, where is the problem is coming from, which is not the case with the GPU. So they tried a couple of things. I don't remember one. I think we had like 2 or 3 time system because they wanted to identify the piece that were defaulting. And I think after a couple of weeks, maybe 3, lost on 1 GPU. So this is another lessons learned because now with the next computer, we'll have a lot of GPUs. So the support is a bit different from what I understand. Any other question? Est-ce quelque chose en ligne?
I have a technical question, so you'll be able to reply online, I think.
Okay.
Yeah.
No? Well, thanks everyone for attending our session. It's been a pleasure to to learn all that. If there's anything, you can come and see us, ask questions. You also have the coordinates of all the presenters. And now I am freeing you to break time. Have a coffee.
And thank you to our presenters.
Oui, merci à tout le monde.
Well, for instance, DFO was interested as well. So we invited one representative to follow one of the cohorts to allow her to see how it would apply to her own clientele. And we put her into contact with the service provider, and they'll have access to our recordings as well. So the recordings of the sessions. Yeah.